Solutions are when two or more substances are physically mixed together. And so when you have a mixture, you don't actually have a new chemical substance. You just have different substances that are now physically next to one another. What we're mostly going to be concerned with are homogeneous mixtures, and that's what we call solutions. When something is a homogeneous mixture or a solution, it means that down at the particle level, you actually have uniform composition. So if you dissolve one scoop of salt into water, then the ions will separate, and anywhere in that glass of water, it will be of equal saltiness. Or you could use sugar as a simple example, or ethanol in water to make an alcoholic beverage. All of those things down at the particle level, the molecules, the atoms, the ions, the things are spread evenly throughout that solution. So that's what a solution is. A heterogeneous mixture means when you've mixed things together and the composition of the solution is not uniform. So there are lots of examples of these, but they tend not to come up as often in our chemistry questions, our chemistry class. Our most important focus is going to be on solutions. Now, when you have solutions, some other important terms are things like solute and solvent. And a simple way of thinking of it is the solute is the thing that gets dissolved by the solvent to make a solution. The solvent is the one that's generally present in a larger amount, and it's the one that has the same phase as the overall phase of the mixture, whereas the solute is generally in smaller amount and maybe changes phase when it mixes into the solution. Our most common type of solution that we're going to look at are aqueous solutions. That means that water is the solvent, but there are lots of different kinds of solutions, maybe that you wouldn't even think of as solutions. Like regular air all around us is technically a solution. You'd probably say that nitrogen is the solvent because it makes up about 78% of the atmosphere. And some of the solutes are oxygen and carbon dioxide and whatever other gases are floating around us. We also have salt water is an obvious one. There's lots of dissolved solids in ocean water. Even tap water is a solution with very low concentrations of lots of different ions. You can have carbonated beverages where a gas is dissolved into a liquid, and the carbon dioxide that's dissolved is aqueous, and then it slowly bubbles out as gas. So you can have different phases together in the same mixture. So lots of different examples of these homogeneous mixtures, these solutions. Now, you're expected to know some idea about solubility. That's trickiest for covalent compounds. Well, with covalent compounds, the simple rule is that like dissolves like. Things that have similar intermolecular forces will tend to be soluble or miscible in one another. And if they don't, then they will be insoluble or immiscible with one another. So polar things tend to mix well with polar things. Nonpolar things tend to mix well with nonpolar things. And things that hydrogen bond mix well with other things that hydrogen bond. So a big focus is water solubility. Things that can hydrogen bond with water molecules will tend to be water soluble. So that includes things that have OH groups, but also things that just have C to O bonds or C to N bonds, because having that O or that N allows the molecule to form a hydrogen bond with the H of the water molecule in its OH bond. So that's really the key to being water soluble. Things that are going to be fat soluble or nonpolar soluble tend to be things that are mostly hydrocarbon, things like benzene or hexanes, things that mostly are just C and H, because they're extremely nonpolar. They won't mix well with water, but they will mix well with one another. When covalent compounds dissolve, for the most part, they're going to make solutions that are non-electrolytes because the molecules are neutral and have no overall charge. So when they mix into water, there's not a high amount of charged particles free to move in the solution, and therefore the solutions don't conduct. However, when we take ionic compounds, we know that they're water soluble. They're water soluble because of the ion dipole interactions that they can have with lots of water molecules, the polar water molecules. And when they dissolve, they are going to be electrolytes because once you dissolve an ionic compound, you do have charged particles that are free to move in the solution, and those are the ions. So solutions of ionic compounds are electrolytes. And we usually can dissolve more of a solid, an ionic compound, or a covalent compound, but especially ionic salts in solution when we raise the temperature of water. This is partially because the water molecules are moving faster and can keep the ions surrounded more effectively. It also has to do with sometimes dissolving ionic compounds is endothermic. And so by providing heat and raising the temperature, we encourage that process and we favor that process and allow the particles to be separated. When we talk about ionic compounds being dissolved, we use a term that they are fully dissociated. So fully dissociated means that the ions have fully separated from one another and have become hydrated and surrounded by the water molecules. So a way to represent that in a chemical equation would be to take NaCl and to dissolve it. It actually means that the Na pluses and the Cl minuses are separate from one another now that they're in the solution. So a lot of times in chemical equations, you'll see ionic compounds represented like this on the left. They'll be written together like NaCl, sodium chloride, aqueous, and you're supposed to understand that what that actually represents is that the ions are separated from one another, even though they might be written together. And that also means that you have to look for the subscripts becoming coefficients. So MgCl2, when that dissolves, for every one MgCl2, you're going to get one magnesium ion and you're going to get two chloride ions in the solution. Iron 3 nitrate will give you one iron 3 plus ion and 3 nitrate ions in solution. So understanding that ratio and how many ions it dissolves into is another important aspect of ionic compounds forming solutions. Finally, the other bonding types, the metallic bonding and the giant covalent solids, tend not to be soluble, certainly not soluble in water. And in general, we wouldn't consider them to be very likely things to dissolve. Although when we form alloys, which are mixtures of metals, those are actually solutions of metals mixing with other metals. But in terms of our traditional water solubility or nonpolar solubility, metals and giant covalent solids, for the most part, won't dissolve. And the last and maybe the most important aspect of solutions for the IB exam has to do with concentration. Concentration is how much of a solute is dissolved in a given amount of solution. We have sort of vague terms like dilute and concentrated, with dilute meaning low concentration and concentrated meaning high concentration. But obviously there's a whole spectrum of concentration that you can have. So it's important for us that we quantify it. The most common unit for the IB is molarity, which in an American system would just be given a capital M, and it would stand for the moles of solute per liter of solution. But being the IB exam, we're going to be using the decimeter cubed. So the concentration unit is moles per dm cubed. So that refers to the moles of solute that have been dissolved per dm cubed, decimeter cubed of solution, not just of solvent. As an equation, we can represent that as C for concentration equals the moles of the solute divided by the total volume of the solution in decimeters cubed. This will also allow us, if we rearrange that equation, to solve for the moles of something if we know its concentration and its volume. So, for example, a 1 mole per dm cubed sodium chloride solution means that there's 1 mole of sodium chloride dissolved in every 1 dm cubed of solution. But it could also mean that we have a half mole in a half dm cubed of solution, and so on. So concentration gives us a ratio, and I could have a 1 molar solution and I could pour out 10 mLs of it, or I could have a whole liter of it, or I could have 2 liters of it. The concentration gives me the amount of solute per volume of solution. A 2 molar solution is twice as concentrated because it has 2 moles per 1 dm cubed. So doing calculations with solutions is mainly going to involve this N equals CV equation, which is going to be very important for the IB exam. There are a couple of other units of concentration. They get used a lot less by the IB, but they are important, and you are expected to be aware of them. One is grams per dm cubed. So it'd be pretty simple to convert into this from a mole per dm cubed. You'd just be doing a mole to gram conversion, and then you would be in grams per dm cubed. So how much mass of something is there per dm cubed of solution? So if you multiply the concentration by the molar mass, you'd be in this unit. And that unit isn't used very often, but why it might be important is that it's a step along the way in getting you to the unit of parts per million. So ppm, or parts per million, is a concentration that's often used for very, very low concentrations because it makes the numbers a bit simpler. We avoid using very small decimal numbers. So this is the grams of solute per million grams of solution. So when you have something that's grams per dm cubed, in a dm cubed of a normal aqueous solution, a liter or dm cubed weighs a kilogram, weighs 1,000 grams, more or less, unless it's super concentrated and maybe it's more dense than water. But for water, 1 dm cubed weighs 1 kilogram, so weighs 1,000 grams. So when you have how many grams per dm cubed, you really have how many grams per 1,000 grams of solution. So how many parts per 1,000 would be another way of thinking of grams per dm cubed. So parts per million is, well, then how many parts are there per every million grams of solution? So the difference between grams per dm cubed and parts per million is just a factor of 1,000. Instead of how many grams per 1,000 grams, we now want to know how many grams per million grams. So to do that, we just have to multiply that concentration by 1,000. So if we can do one little quick example here. Okay, so if we had a 1 mole per dm cubed solution of NaCl, we wanted to convert that. Well, 1 mole of NaCl weighs about 58 grams per mole, so that would be a 58 gram per dm cubed solution of NaCl. It would be the exact same concentration, just expressed in a new unit. I take the molar concentration and I multiply it by the molar mass. And then to convert that into a parts per million would be that there are 58,000 parts per million of NaCl. So that means that out of every million grams of solution, there are 58,000 grams of NaCl. So you can see that unit's probably not going to be used for something on the scale of molar, because you get these huge concentrations. So for something like salt water, we normally use molarity. But for something like the ions dissolved in tap water, then you might see parts per million, because then you might get something like for oxygen having 6 parts per million of O2 is actually around a normal concentration of dissolved oxygen in an aquatic system, in a body of water. So 6 to 8 parts per million or something like that. So really, really tiny amounts of water. And this makes more sense for water, because if you have to convert that to a gram per dm cubed, now you're looking at 0.006 grams per dm cubed oxygen, and then that would be even smaller as you convert into moles. So these different units of concentration have different uses, and you're expected to be able to convert between them and to use N equals CV to work with moles and concentrations and volumes.